Hi everyone, welcome back. I am excited about this video because this is one of my favorite topics going back like even 10 years ago when I tried to build something for what we used to call back in the day was content-based image retrieval, which is basically, hey, you have an image and it's got certain features and you want to extract all other images with very similar features because in fact 10 years ago I thought of it from a oil and gas exploration point of view because there are certain images when you actually look at the core samples and it's got certain porosity and the texture looks one way, and then you're like, I know I've seen this somewhere at some other location, right? So you may be looking at, I don't know, a Berea sandstone. So for those of you from oil and gas background, you may understand this. So that sandstone has some type of a look. I've done a project in, I don't know, in the past where the images looked somewhat similar to this. So it can go ahead and retrieve that. Anyway, this was my vision like 10, 12, 13 years ago. And the tools at our disposal were not as cool. Now we have much better tools with deep learning. And in fact, in the next couple of videos, I'm going to talk about an extension of this, which is FAISS. I'm not going to talk about it right now. I'm just mentioning that. So what you see in this tutorial is going to be the first implementation of image similarity search. And here it's very simple. It's literally a few lines of code. You'll be amazed at how easy it is for us to build these things with just a few lines of code. And I'm going to walk you through the process in the next 3-4 slides. But if you're like me, you probably hate PowerPoint presentations. That's why we will jump into code right after the initial introduction. But of course, getting a good background is very important. So the goal is to have a search engine based on an image, which kind of searches your own database or whatever you want to call it, your own list of images, and then highlights which ones are ranked top. Okay, so how do we approach that in general? Like for this tutorial, we're going to focus on a simple architecture. Here I'm talking about VGG16 as simple architecture. Literally 5 years ago, this was state of the art. It's amazing, or not even 5, like 6-7 years ago, I would say. And it's amazing how technology gets so old so fast nowadays, right? Okay, I get to go on these tangents. I should focus. Okay, focusing back, VGG16 architecture, very simple convolutional neural network, as most of my regular subscribers know. If you're not a regular subscriber, please subscribe right now. Pause the video, hit the subscribe button, and while you're there, try to find the thanks button if you're feeling extra generous. But yeah, subscribing really helps you by putting these videos in front of your face rather than searching for them. Okay, like I said, talking about going on a tangent. From now on, I promise to focus on what I plan on actually talking about. Okay, this is a simple convolutional neural network. And VGG16 got trained on ImageNet, like many other architectures, deep learning architectures, which means you can actually cut this off, this architecture, at any point and take those as your features, right? So to search for images, you need to capture those images, the content of the images, as a vector or something that represents the image, typically a feature vector. And there are many ways you can get the feature vector. You can get your own feature descriptors, like you can use Gabor filters, you can use edge detection, and you can combine all of those into a single vector if you want it. Or just take something pre-trained like VGG16, pre-trained on ImageNet, and chop it off at some point. For example, at the end of it, if you look at right that location, if you just take the remaining part off, the classifier part off, what you get is a vector of size 512. So it's a bunch of numbers of size 512. And that represents the features contained in the input image that you actually have, right? So just imagine now taking an image, for example, obviously, when you query an image, it's also 512 length vector. So you're storing, instead of this entire image, you're actually storing a vector representation of each of these images that are basically a feature vectors, right? And then the query image is matched against them. Now, how do you match an image? It's not an exact match, right? So it's not like you're saying, okay, hey, my vector has values 2, 3, 4, 1, 5. and then you have another image that has values 2, 3, 4, 1, 5, then it's an exact match. That's okay, that's easy, but you'll never have that. These are all feature vectors. You have like some stream of values, 512 values, and you have another stream of 512 values. How do you compare those two? This is where the feature comparison, like using cosine, comes in, but I forgot I introduced this slide, so let me actually talk about this vectors in case you are still unsure of what these 512 vectors actually mean. Each value means something, and if I plot it, this is literally a plot of what you see up here. I took each of these images, sent it through a VGG16 pre-trained network, exactly like I showed you in the last screen, and the values that I got, I saved them in a HDF5 format, and this is just a HDF5 viewer. Basically, I'm opening this, and you can see for each of these images, I have a entire vector. So x-axis here is the full 512 values. Obviously, this value is much higher than the one next to it, and so on. But it doesn't matter. What you need to do is match the pattern of your test image with one of these images, and then rank them based on what gives you the best match versus the second best, and so on. Right. So this is how the search needs to work. Now, how do you compare these vectors? That's what I was trying to explain earlier before I saw this slide. How do you compare vectors? Well, there is something called cosine similarity. There are various ways, by the way, right? You can use L2, you can use a bunch, but cosine similarity is the most intuitive one. So I want to start with this. So what does cosine similarity mean? What does cosine even mean? Well, you know, a cos theta is adjacent side by hypotenuse, right, in trigonometry. But when you look at vectors, it's very similar. So what is cos theta? When you have two values, A and B, like when you have two vectors, cos theta can be a dot product of these two vectors divided by the magnitude of those two vectors. So that's how theta is actually given. I think I explained that here. But cosine similarity, in that case, the cosine compares the how aligned these two vectors are, right? So you have to think about what is cos of 0 is, cos theta, cos 0, and what is cos of 90 degrees is, what is cos of minus 90 degrees is, and so on. And you know that the cos theta values go from -1 to +1, right? So you can say any value that is equal to 0 is not aligned. I mean, it's not a match. Any value that is 1 is a match, and so on, because they both are fully aligned. Cos of 0 is 1, right? So if both are aligned, then you get a value of 1. If both are perpendicular, that means they're not aligned, then you get a value of 0. And if both are opposite, if the input image is opposite of the actual image that you actually show, then the value would be -1, right? Cos of. Okay. It measures the cosine of the angle between the vectors, and as you know, the cosine I just mentioned, it's a dot product of these two vectors divided by the magnitude of these two. That gives you the cos theta value. That's it. It's as simple as that. You have a simple formula, and then results range from -1 to 1, like I already mentioned, and value of 0 indicates perpendicularity. You know that cos of 90 degrees is 0, so there is no similarity right there between those two images. And all we do is compare the query vector against a database of all vectors. So it's a brute force, meaning you have one query image and you have 10,000 images. You're actually looking at cos theta of comparison between this and each and every one of those 10,000 images. It may not be efficient, but it works great. Okay. And that also assumes that you already have the feature vectors extracted from those 10,000 images, right? You need to index them somehow. Okay. So since we cannot visualize all the 512 values like in the vector, what I did here for visualization purposes is collapse the 512 into 3 most important dimensions using principal component analysis. I've done videos on PCA in the past. All you do is you combine, you kind of find the 3, you remap your 512 into 3 principal components, and those are the ones I'm mapping. And this is just for visualization purposes. Yeah. And like I mentioned earlier, you can also use L2 distance instead of cosine distance, but cosine is easy to explain, like I just did. Hopefully you found that to be easy. And here is a screen, the result, we'll see that in action in a minute, where my actual database query image is in red. This is where my input image falls in this 3D space, And then these are the top 3 matches. Tiger 1, Tiger 2, and Zebra is top 3 matches. By the way, my input image is a tiger, and Zebra kind of has features that matches with tiger, so it shows up right here. And all these other dots, again, I only have 13 images in this example data set, so you see how the other dots fall very far away, and these are the ones that are a tight cluster right there. Okay, so now I want to end with a teaser for the next video. Basically, here we are comparing our test query image with a whole bunch of other images, right? Only 13 images, fine, who cares? This approach works great. 1,000 images, this approach works great. Maybe 5,000 images or so, this approach works great. What if you have 1 million images that you want to search against? This is brute force, it takes forever. For every search, it takes forever. Okay, we are going to quantify that in the next video. So what if you really want to compare this on very large data sets? So how can we create an efficient way of doing these? And that's exactly what FAISS does. This is again a teaser, so wait for the next tutorial. But for now, let's understand the VGG16 with Cosine, which works great even for thousands of images on even my laptop, right? It's not even a big desktop or anything. Okay, let's jump into code. And here is my code right here. Now, I divided the code into 3 separate aspects, like files for easy demonstration purposes. If you want, you can combine them into one. But one is feature extractor, right? What do we need? We need a way of extracting features using VGG16. And once the features are extracted, we need a way to index them. You see how few lines each of these, actually, this is like 50 lines of those. Half are commented, and the remaining half, other part is just the top part over there. And the same thing with my indexing. It's literally a couple of lines right there. And also for querying, I added the plot, but its actual query is 5 to 10 lines or something over there, right? So this is very straightforward, not an elaborate process. Let's start by understanding the features, and I commented this out, but let's go ahead and look at, let's actually run these. I want you to understand VGG16 features. So let's import our libraries, TensorFlow and all that. And why is it taking so long? I don't know. This is just importing libraries. Let's give it another few seconds. I'm doing many things on my laptop, and it probably doesn't like what I'm doing here. Anyway, it imported the libraries. So what we're doing here is actually for VGG16, we are getting the ImageNet weights, and our input shape is 224 by 224 by 3. That's how that's the input that VGG16 takes in. And let's go ahead and print the model summary. Okay. And include top equals to false basically means, hey, don't use the classifier layers and only report the layers before the classifier, right? All the way until the max pooling. And it printed that out over here. And this is what I showed you earlier in the PowerPoint presentation. So as you can see, the input image is 224 by 224 by 3. Very simple, straightforward model. I love these models because everything makes sense. With convolutional 2D, you're adding 64 features. You're adding 64 features again, and you're adding 128 features. So it makes sense when you go through this. It's okay. All we care about right now is what's in the last, and at the end, it gives you 512 features. Right? So we take our input image, a 2-dimensional, probably a color image, which means 3 channels, and you send it through this network, and what you end up with is the 512, a vector of size 512. Okay, so with that information, let's now you understand what's going on when you bring this model. I'm going to comment that out. Code will be available. Look under the description so you can play in your own time. Okay, so you don't even need to use classes if you are not feeling comfortable with that. You can just define a function and get away with that, right? So I'll leave that to you. But what we are doing here is the input image is 224 by 224 by 3 is what it expects. So your input image, it doesn't need to be that. When the image goes in, it's going to be resized anyway, right? So that's what we are going to do here. You see, that's what we do when we load an image. We put a target size. Target size is basically your 224 by 224 by 3. That's your input shape. And then everything is fine. Okay, so we are loading the image and we are converting that into an array, and we are expanding the dimensions by 1 because obviously you know how for those of you who are new probably to this field, a little bit of explanation helps. So basically until that point your image is 224 by 224 by 3. We are expanding the dimensions because we want to add that specific dimension, because these models are built to accept multiple images as a batch going in. In our case, we may have only one or we may have a batch. So we need to expand the dimensions right there. And then you are pre-processing the input to make sure the pre-processing matches whatever the VGG16 expects right there. And then you're providing that as an input to the model and you're predicting on it. And what you get is a bunch of features, and we are just normalizing the features right there. And how are we normalizing the features? We are using a from NumPy linalg. I just abbreviated that as LA, and that's what you're using. So very straightforward. What do you get out of this feature extractor? Basically 512 numbers, features. Now, the next step is indexing your images. So I have a whole bunch, 13 images. Let me just show you. Sorry, I have to use my glasses, getting old. Okay, so let me bring this on to the other screen. So as you can see, I have these images. This is my index images, okay? And my query image is different, just to show you. So here is my query image, and I have 3 different images. This is tiger 3. This tiger is lying down right there. And if you look at all images, I mean, these 2 tigers are standing up, and obviously I hope it would identify tigers as the match, and probably zebras as the next match, and distant matches would be all of these other ones. Okay, now that you know what images we are dealing with. So here again, we are from the feature extractor, we are getting the VGG net. This is what's giving us our features, and then we are going to go through each and every one of these images and applying that model and appending the features and adding those features into an array. That's it, and saving that as a H5 file, HDF5 file. That's it. Okay, so this is our database. Our H5 file is our database, and now we need to search this database for our image, and that's where the query part comes in. Okay, ignore the first part, plotting this feature space, like performing the principal component analysis, because I want to collapse the 512 into 3 principal components, and then plotting them is basically down here, and I'm plotting our different values in different colors. So this is just a plotting part. The actual meat of it is down here. So we are loading our H5 file, which is the file with all the indexes for all the images, like all the vectors for all the images. And then we are also extracting the image names, obviously, so we can actually print out, hey, these are the matches. Otherwise, it doesn't make sense. And what is our query image, which is tiger3.jpg is the query image. And then from the query image, I'm also extracting the features. And basically, this part is the calculation. The entire thing, the matching, the cosine matching and everything is literally that. It's anticlimactic. It's doing something amazing, but all we are doing is, hey, we have a query features and we have a features for each and every one of the images. Go ahead and measure the cosine distance. And once you have the cosine distances, now I'm going to sort them based on the value. And I'm going to basically say, hey, the highest value is the one that is the best match, and the least one is the one that's the least match. And that's what I'm printing out down here. Okay, so that's a lot of talking. Let's go ahead and index it. Let me clear the screen. Oops, sorry, where did I type? Okay, I didn't mean to do that. I wanted to type here, clear the screen. So we start with a clean slate and go ahead and run our indexing, and it should extract features. There you go, from each and one of these images. If you have 10,000 images, this is going to be a slow process, obviously, right? But once indexed, the search is not as slow. It's still slow compared to the state of the art, but it's still not as slow. Okay, there you go. So all the features have been written from all the images, and now we are ready to perform a query. Let's go ahead and try to match tiger 3 with these images. So it's going to match right now with all the feature vectors. It's calculating the cosine, and it basically said, okay, the first match is tiger2.jpg without tiger3. And I don't know if you need to see these images again, but yeah, tiger2 is that one. Yeah, so this is the match, and tiger1, and then zebra2. Zebra2 is right there. So these are the top matches. The other ones it didn't even recommend. In fact, just for the sake of completeness, let's do what is it called, histo.jpg as the query image, and hopefully we'll see the histo images, right? So histo.jpg is our query image. Let's go ahead and run this. And there you go. So what the top three matches are: 4.jpg, 2.jpg, and 1.jpg. Yeah, very good scores actually, 0.7. So what are they? So 4.jpg, 1.jpg, no, 2.jpg, and 1.jpg. And in fact, if you look at it, 4.jpg has a lot more pinkish color and the texture. And if I actually go back here to our query image, it kind of looks very similar to our 4.jpg, right? So you can see how this is actually working. So I hope you learned something new, and this is actually very ready to implement. You can implement this. In fact, you can put a quick GUI using PyQt5 and deploy this. But again, please remember that this is efficient, in fact, up to about a few thousand images. But once you have more images, you need a more robust way of handling this, and FAISS is the best way, FAISS. Please stay tuned for the next tutorial, because that's where I'm going to provide some introduction to FAISS, and then we'll put that to use for our image retrieval code. So thank you again. Do not forget to subscribe so you get notified, and also turn the notifications on so you know when my next videos get released. Thank you.